Hello class, this is Ms. Riggins coming to you today with today's video on section 7.3, tables of integrals. As you're watching the video, please make sure to write down important information, formulas, statements, equations, or graphs in your notes, and feel free to pause, rewind, and replay the video as often as you need. And then at the conclusion of watching the video, write a brief summary of what occurred in the video and submit that summary via the online WISC form the day before class. All right, let's begin. This video is going to be chock full of examples because that's what you're requested, but also because that helps you see different strategies on how to use the table of integrals to solve integration problems. So first of all, in the back of your book, you have a table of inside cover, a table of indefinite integral functions. Although you don't have to memorize them all, it would help that you at least have memorized these first ones. You should have already known these first ones, the basic functions, and then you have to be able to recognize when you need to go to the table of integrals because you've recognized some form of the problem that you can use the table of integrals with. Table of integrals is broken up according to your book into 5 sections, I believe. 1 is the basic functions. 2 is the products of e to the x, cosine of x, and sine of x. So if you have integrals that involve multiplying e to the x and sine of the x, or e to the x and cosine of x, or just cosine of x and sine of x, table integrals is for you. If you have problems involving a polynomial being multiplied by either natural log, e to the x, cosine of x, or sine of x, then this is section 3. And then if you have integrals that involve powers of sine of x and cosine of x individually, then you would use section 4. And then if you have problems involving quadratic functions or type expressions in the denominator, you would use section 5. Oh, there's actually 6 sections. And then if you have problems involving the square root of some type of quadratic expressions, you would use section 6. Okay, I'm only going to give you examples from, I think, the first 5 sections, just so you know. Okay, these examples are coming straight from your textbook, which has more detailed written solutions, but I just wanted to, so you can use that as a resource too. So we take a look at example 1, which is find sine of z, 7z times sine of 3z dz. Well, I recognize that going to my table of integrals because it's a product of sines as section 2, number 10, which looks like this. So I need to identify what A is and what B is, and as long as they're not equal, I don't have to go through a integration by parts strategy or substitution strategy. I can just use the table of integrals to get my indefinite integral solution, which is essentially just this. Okay, so in this case, A is 7 and B is 3, and I can just substitute my A and B into this problem and get my answer, and that's sufficient. Example 2 involves a polynomial times e to the 3x, which means we would use section 3, and we would define that one. That's actually number 14 in section 3, a polynomial times e to the alpha x, and e to the alpha x, where in this case alpha is equal to 3. Now here's the tricky part, is that as you can see here, you're going to have to take the derivative of the polynomial, and since this is a 5th level derivative, we're going to have to keep applying this process for at least 4 times, because we have 4 derivatives until we get down to x. So as you can see here, we'll apply this for p prime, p double prime, and vice versa. So in order to use that in this problem, that's what we would do. Okay, oh, the solution. I forgot to show you the solution for the first one. So using this is the solution. And using this is the solution for the second one. And again, this is because we had to take the derivative several times. So this is the p value, this is the p prime, and this is p double prime, and this is p triple prime, p to the 4th prime, and then we're left with a constant. Okay, so it does stop looking pretty. Oh, also you have to alternate the signs. So you start off with negative, or subtraction, and then you do positive, subtraction, positive, subtraction, and of course there's always plus c. All right, another example, find cosine of 3 cosine cubed t times sine to the fourth t. Well, we have a section in section 4 that's a result of multiplying cosine and sine, but it's a little bit more evolved in that case because it depends what these powers of cosine and sine are. So in this case, if m, the power of cosine, is odd, then we're going to use a substitution method and we're going to let w be equal to cosine of x, okay? And once we do that, we get then dw is equal to cosine t dt, okay? And then cosine squared t is equal to 1 minus sine squared t, 1 minus w squared. Why do we do that? Because we can break up the cosine cubed into a cosine squared and into a cosine, okay? So we're breaking this up into this, into this. And the reason being is that we want to be able to use u substitution. In this case, w substitution. So cosine squared, because w is sine t, ends up being 1 minus w squared. This is my w to the fourth power. And then my dw is cosine t dt, which is why we broke up that cosine, took out one cosine so we can be left with a dw, okay? And when we do that, we end up with integral of w to the fourth minus w to the sixth. That's a basic integral, and we can apply our basic integral to get our solution, and then undo the substitution for w to get the final answer, okay? Another example, example 5. In this case, what if m is not odd? What if m is even? Well, the instructions for if m is even says, well, if n is odd, which is the power of if both m and n are even and positive, then they say to convert all to sine of x or all to cosine of x, okay? So we're going to rewrite this so that it is all cosine of x or all sine of x. So I did that down here. So cosine squared x is the same as 1 minus sine squared x. And so then now we get sine to the fourth dx minus sine to the sixth dx. And so we can use previous integrals or our table of integrals formula from number 17 to be able to come up with an expression for each of them. And as we can see here, we just apply that value and we get our final answer. Simplified as well. Not pretty, but at least we don't have to do all the grunt work. We can just say by the table of integrals, we can use this integral formula, antiderivative formula solution, and be done with it. All right. Now we're going to talk about the more challenging ones where what if it doesn't look like anything in the table of integrals? Well, it may be because you may need to transform the integrand, which is the function inside the integral, into something that it looks like using some algebraic manipulation. And we're going to use some examples. One example is we may have to use factoring to do that. So I can take this denominator and factor this denominator into x plus 2 times x plus 4. And then that looks pretty much like section V, verse 27, which looks like this. And in this case, my A is -2, my B is -4 because it's A minus, my C is 3, and my D is 7. And I just use the table of integral formula to come up with this solution. So this is the solution. Okay, so you really need to know the table of integrals to know when you can use the table of integrals for a problem. If you don't know what's on the table of integrals, you won't know if you need to use it. We can also use long division to get our integrand into an expression that allows us to use the table of integrals. As you can see here, whenever the power of the numerator polynomial is greater than the power or equal than the power of the denominator polynomial, we can use long division to kind of break up this polynomial. And when we do that and use long division or synthetic division, we get that this is equal to 1 minus 4 over x squared plus 4. And then we can use from section 5, number 24, because this looks very much like 1 over x squared plus a squared. In this case, a is 2. So we end up with this expression, integrating x1 dx, which is x, and then this is our solution based off this value right over here. Okay. And we can also use completing the square by rewriting the quadratic in this form. So in this example, this cannot be factored, but what we can do is we can use completing the square to write it as a completing the square form. And then we can use W substitution to represent that as W1 over W squared plus 5. And then we do know that based off of basic integral as well. And this is what we use to get our answer. The last step is substitution method. In this case, we know that this looks very familiar to number 8, but the only difference is that this is a b value, and here we have a 5t plus 7 expression. So what we can do is we can let w be equal to 5t plus 7. And then we end up with dw being 5 dt, but we can solve for t. And we can rewrite this totally so that it's in terms of w in such a way that we can use our basic formulas to come up with a solution. This right here is essentially a constant value that we bring out. Not the whole thing, but just this part is a constant value that we bring out. So we're just like this, and we can use section 2.8 because it's exponential times sign to come up with a solution formula. And again, it doesn't look pretty, but this is our solution. Okay. All right. I encourage you to look at the other examples that we didn't get a chance to go through, so you can look at some things as well as understanding strategies. And that's about it.